Okay, folks, we're going to get into what I think hopefully should be some pretty common ground, getting into this thing we call heat capacity. So learning goal 5, know the various equations for constant volume heat capacity and its relationship with temperature. Okay, let's find the slide. Here we go. So we're going to keep invoking these various scenarios that I referred to in the last video. And these scenarios describe different paths that we might take, like something that's isothermal. Or in this case, we're now interested in constant volume. And so what's important to note here is there is no work done when volume is constant, right? There's no change, there's no force being applied over a distance. So when the volume is held constant, referring to the first law here, dW becomes 0, and thus du equals dq. And then now, of course, integrating both sides, we get delta U being equal to just qv. So the little v that we show right there denotes something is being held constant. So in this case, volume is constant. So we want to get used to seeing that when we have that little subscript there. Okay. So this gets us into calorimetry, the study of heat transfer. And hopefully these equations are somewhat familiar to you. So if we look at probably the most simple way we can calculate heat capacity, that's going to be equal to CV delta T, and this is extensive. So if we look at the unit of CV here, that's going to be units of joules per Kelvin. And then now, of course, my temperature rise is units of Kelvin, so that gives me just units of joules. And so that's extensive because if we have 1 gram versus 100 grams, the 100-gram sample is going to be able to hold on or transfer more heat. Okay, so there is an intensive way that we can look at this. So the intensive parameter would be to either look at the specific heat capacity, CS. So let's write that down. Specific heat capacity. And my hope is that that's the one that's familiar to you. So for example, with water, that specific heat capacity is 4.184 joules per gram per degree C or Kelvin, right? The degree C and degree Kelvin, or 1 unit of Kelvin and 1 degree C is the same thing. And so that's intensive because now that's joule per gram, okay? And so this, in Gen Chem, I call this the MCAT equation, right? Because it kind of looks like it spells M and cat. So then obviously this would have to be the mass of our sample in grams, and this would be our temperature rise in Kelvin. We can also come up with an intensive parameter, CVM, which would be joules per mole per K. Okay. So all of these equations stem from the fundamental definition of heat capacity, which is the following. So this is a partial derivative. So that denotes the deltas, right, the partial sign. And then we can also see that volume is held constant right there. Okay. So the way that we can now expand out on these partials, right, I could separate them and write CV dt equals du. And thus we can see this is where that equation comes from. We know that du is equal to qv. And if we integrate dt from t initial to t final, it's going to become delta t. Okay. So now if we look at a graph of u versus t over a large range, so let's suppose we start from like 0 Kelvin, maybe all the way out to like 10,000 Kelvin or something ridiculous like that, okay? So there's going to be curvature in this relationship, right? It's going to look kind of something like this, and generally will increase with increasing temperature because of our relationships, right? 3/2 RT for an atom, or 5/2 RT for a nonlinear molecule, or 3 RT for a linear molecule, right? So U increases with T. However, if we look over a very narrow range, so like let's say, something from point A right here to point B right here. So we can see over that narrow range, a single slope value is going to be a good representative value for that heat capacity. So thus the slope of this graph gives us CV over a relatively narrow range. If we wanted to look over a bigger range, we would need some kind of an equation to describe CV, or we would have to specify at what temperature is this CV referring to, right? So over this narrow range, you can see that that might correspond to like room temperature, for example, or plus or minus 10 or 20 degrees, something like that. Okay. So now, moving on, how do the molecular modes of motion affect heat capacity? Well, again, we noted that this is a partial derivative, so I can play with it in the following way. I can make it say du equals CV dt. That's one way I can play with this equation. Another way I can play with this equation is the following. I can say CV is the partial of t with respect to u as a function of temperature. So we can take the derivative of u as a function of t. And notably, for atoms, or really monoatomic gases, right, we know that u of t was equal to 3/2 RT. And now let's be specific. We know that that's technically um, okay? So now if we want to take that derivative, and because that's we have to make this CVM, all right? That's going to be the partial of t with respect to 3/2 RT. This is a very simple derivative to take, right? That's just going to be 3/2 R, okay? Equals CVM for a monoatomic gas. Well, what about a nonlinear molecule? Well, recall that UM for a linear gas molecule, I should say, was equal to 5/2 RT. So again, another very simple derivative. So that means for a linear molecule, CVM is equal to 5/2 R. Brilliant. So let's put that down. Monoatomic gas. This would be, I almost wrote nonlinear, but it's linear. And then finally, for a nonlinear, hopefully you can see how this is going to go. The internal energy of a nonlinear gas is 3 RT. So that means taking that very simple derivative, we just get 3R for CVM for a representative non-linear molecule. So what that means for us is a non-linear molecule can absorb twice the amount of heat as a monoatomic gas without a rise in temperature, right? That's what the heat capacity is all about. If we look at that unit of CVM, right, it's joules per mole per Kelvin, or for CS, it's joules per gram per Kelvin. So in other words, that is how much heat something can absorb to increase 1 mole by 1 degree Kelvin. Or in the case of CS, how much energy can that thing absorb to bring 1 gram of that material up by 1 degree Kelvin. And again, because the nonlinear has twice the heat capacity as the monoatomic gas, it can store twice the amount of heat without a rise in temperature. And it's storing this in, you guessed it, its molecular modes and degrees of freedom. Okay, so there will be another type of heat capacity for gases that we describe, which is CP, the constant pressure heat capacity. But before we go down that road, I want to have another brief video on the heat capacity of solids and liquids. Okay, folks, I'll see you then.